Okay, hi. So first of all, I would like to apologize because this talk might annoy both the communities here, the modelers and the people who are waiting for the direct detection. But the reason that I'm taking this direction is simply because we haven't had a detection yet. And suppose you have a detection, when you have a detection, suppose the detectors are online, suppose it's at a good location, suppose you are able to reconstruct it correctly, then you might be able to have a good information about how things are going on. But then again, to refine that information, you might have to wait another 50 or 100 years. So in the meantime, if Einstein Telescope is there and you have tens of thousands of binary neutron star mergers and binary black hole mergers in millions, in the number of millions, then we could use that as another parallel tool to constrain these parameters. So essentially, as we all know, there are several evolutionary parameters for compact binary evolutions, and these are highly unconstrained. They have still high level of and there are also multiple degeneracies which still exist. Now, the core collapse supernova engine is one of the things that affects the binary merger rates. And then you can see the rate is also affected with the evolution of redshift, with redshift. And with the LIGO-Virgo detections, we have already shown that the GW observations can constrain these merger rate densities. And if you have strong constraint on these merger rate densities with redshift, you can constrain the evolutionary parameters. So essentially, the logic of this work is to constrain the core collapse supernova engine parameters by excluding the binary evolution models. So this idea of using merger rate density to constrain the binary parameters, evolution parameters, is not new one, but essentially up till now we are not able to fully exploit the potential of this idea, simply because we don't have the reach that we need to implement it. So what I show here is O3b and O4a sensitivities, and you see during O3b the best detector had around 130 megaparsec for BNS. During O4A, it was improved and it went around 160 or so. Now, just as an example, I show on the right top plot the population, one of the population models, and you see that it is well understood that the merger rate densities kind of trace the star formation rate. So most of the models are expected to peak around redshift of 2. Now, in the bottom plot, you see where do we stand? The green is O3, 130 megaparsec. Then we go a little bit higher to 160 megaparsec. A plus will be 340 megaparsec, and A sharp will be 500 megaparsec. You will still be at redshift 0.1. To probe the full population, you need to go to up to redshift of 2. Now, this is a plot that was made by Mundell and Floor, and they compiled all the binary models that have been generated since 2010 up till now. And just forget the bottom portion of the plot and look at the isolated binary evolution. And you see that the merger rate density, just the local one, has a variation of about order of 4. So essentially, the local rates also vary by orders of magnitude. And meaning, what is the probability that the combination of population parameters will give you exact merger rate density over all the redshifts? So as an example, what I show here is I picked up, just ran 20 models from a particular paper, and I show how the constraints were using the first gravitational wave catalog. So the x-axis is the BBH merger rate density that was predicted by the catalog, and the left is the BNS merger rate density. So essentially, you are able to exclude some of the models, but keep in mind these are only the local merger rate densities. Then comes the second gravitational wave catalog, and the area seems to shrink and you exclude more models. But then again, the another point to keep in mind is whatever models might be allowed by these constraints might not be the ones that produce the merger rate densities at high redshifts. Now, this is third gravitational wave catalog. The area has changed. Now, it hasn't shrunk, it simply changed. So now the models which were excluded earlier are now allowed. So the reason for it is this: when we predict the merger rate error bars, so you have to assume a certain mass distribution And this assumption on the underlying mass distribution changes the error bar that you have on the merger rate densities. So essentially, what I show here is the assumption that was made by LVK papers, power law plus dip plus break model, the multi-source model, the bin Gaussian process, and you can see how different the merger rate densities are predicted by these different assumptions. So essentially, currently GW observations have very weak constraints on even the local merger rate densities. The merger rate densities up till redshift of 1.5, they are highly dependent on what mass distribution models you take into account. And then, so essentially, we can't use, it's good to have an idea of the merger rate constraints, but you can't use them to confidently exclude the binary models. So now we have to see, can ET do better? So for this, what I did is I took some of the models. For this presentation, I'm showing 12 models, population models, which probe different population evolutionary parameters. For example, on the left side, the models are from Baczynski 2020. So you can see that they use a rapid supernova for black hole and neutron star masses. They have different percentage of Roche-Loeb overflow, and then they also differ in what is the definition of solar metallicity, just to name a few. On the right side, we have new models which were generated by Oleak et al. In 2022. They have revised common LOA prescription, and then they also implemented different prescriptions for pair instability supernova limits. And in addition to these, they have new formulas for remnant masses. From Chris here developed them, and they implemented different mixing fractions. Mixing fractions, meaning I'm not a modeler. What I understand is that it is inversely proportional to the convection time, convection growth time, and then the smaller the fraction, larger is the time. So now the question is, can we differentiate between these these parameters? Just to start with, let's look at what are the rate predictions from different models. So here I plot all the 12 models that I have, and you can see some of them are quite far, like an order of magnitude far, but the ones that had these new, wait, is it really 5 minutes? I just started. Okay. So, and you can see the 6 models are quite close. So for the sake of this presentation, I took 2 models, the M30B, which is the bright blue line. You see this one. And then the model which had F05 with the standard pair instability supernova limit. So F05 standard PSN. So it is the red line somewhere in that, somewhere here. So these are the 2 models. So what I did is I take these 2 models, I generate a mock population of these 2 models. Then I establish a certain detection threshold, because you need to specify what you call as a detection. So I specify a detection threshold. Then I estimate the parameters with the, this is supposed to be a movie, but okay. So, so I estimate the parameters of the binary, like the redshift and the chirp mass. And then on the left lower plot, what I show is the posterior that I get from my parameter estimation code. The red dot is the true redshift, and the blue distribution is the posterior that I get for for this particular binary. So now, but then situation is like this. Given the threshold that I set, not all the binaries cross the detection threshold. So in this case, only 15% of the binaries cross the detection threshold. So in both these plots for 2 different mock populations, the red line is the true mock population that I generated, the rate coming from that population. The blue line is the one that crossed the detection threshold. And the green line is the one that I estimate from the redshift in my parameter estimation. So essentially what I'm saying is, if I detect them, we can estimate the redshift quite correctly. But then the problem is that we don't detect them. Even with ET, you lose a lot of binary neutron stars. So the prescription that we developed is that you estimate the merger rate density. You somehow need to know what is the detection efficiency, how many binaries are you losing at each redshift. And then when you know this, then you can take into account and reconstruct the merger rate. So this is what we did. The estimate that we have from our parameter estimation. So we say that this population that we estimate is the true representation of the underlying population. So we say, okay, the chirp mass will be the probability will be the distribution will be the same, the redshift distribution will be the same, and we keep Q as the free parameter ranging from greater than 0 to 1, and then we generate a secondary mock population. Then we throw these binaries at random orientations and we see how many do we detect. So doing this again and again and again at the redshift, we know how many binaries will we lose or detect. So once you have this fraction, you can take this into account and then get the merger rate density reconstruction at each redshift. So essentially, we don't assume anything about what kind of true population is. We just assume that whatever we detect represents the population. So now taking this into account, this is what we get for the two models, M30B on the left and the one with the mixing fraction of 0.5 on the right. So on the left plot, this is a simulation which was done for 7.69 years, and the right one was done for around 6 years. The shaded region represents the Poissonian distribution for about half a month in both cases. Now, once you have reconstructed this merger rate density, the goal is to compare how good, to which model does it match, so that we can actually constrain the models that went in there. So what I did is I calculated the root mean square error with all the 12 models that I had, and this is what I have. For M30B, the red dot shows the lowest error, root mean square error, in both these cases. And you see that it matches exactly with the population for which we generated the mock population. And since the runs were done really recently, so I have copy pasted the output of the code, and it shows what is the RMS error for each value, so the numerical value. So the conclusion is that the binary merger rate density evolution with redshift using ET can provide indirect constraints. These constraints will be strong enough to distinguish different populations. If the merger rates vary at a larger redshift, you need to observe longer, but then it can be done. But yes, if the rates are exactly same for all the redshift range, then you won't be able to distinguish between those two, but you will still be able to put strong constraints on the parameter space. We are also looking at the work of using the binary black hole and neutron star binary black holes to get these merger rate density constraints in addition to BNS. Thanks.
So we have time to get a couple of questions. Any questions? Okay, Chris.
Do you think you'll have enough? There's a lot of uncertainties in the population synthesis models. Do you think there's enough data, especially as you go to high redshift, to disentangle those uncertainties, or will it be like you get clusters of knowledge from them?
So the models that I showed, we were able to distinguish them even with BBH, because if you reconstruct the mock population with BBH, you get a very nice constraint up to redshift of 8. So you can disentangle them. But again, meaning these models don't span over the entire parameter space. So there are degeneracies. So yes, meaning most of the population models use the rapid engine, and then yours is the new one. So yes, if we get new models, then that will be nice.
More questions? Okay. If not, then let's thank the speaker.